in protein purification, you can never truly relax until your protein is cryoprotected, flash frozen, and into the -80 freezer. So I say freezing, but really we like flash freeze them, and we do this in a way that prevents the actual freezing of water to form ice. We add the cryoprotectant like glycerol. What this is going to do is it's going to allow for vitrification, where instead of forming this like solid ice crystals, the water doesn't have time to organize because we do it so fast, and then we have all these glycerol molecules just like making it harder for the water molecules to hook up into the network that they need in order to form this like crystal, which is ice. And so we don't want the ice forming because we have all this water flowing through our protein, and if that water that's flowing through our protein turns into ice, then our protein is going to like crack open. It's kind of like you wouldn't want that happening in your pipes. So this is our like antifreeze, and we also make like aliquots. I'll tell you more about these. So these are like single-use servings of our protein, so we don't have to like freeze thaw them a bunch of times. And yeah, and I want to tell you more about this sort of thing and storing your proteins, keeping them safe and happy, because you can do, there's so many places in the protein purification that can go wrong, and then you're so excited that you're so exhausted, but it's important that at the end of the day, you put your proteins away safely. So imagine a molecular freeze dance. Our goal is to get these molecules to freeze on the spot. But if we give them alert that the freeze dance is coming, then they're going to be able to organize up into like their cliques and stuff in the networks that they like. And if they do this, have this time to pre-organize, and if they're able to find each other easily, then they're able to form these like little groups. And what's going to happen is that all of those water molecules, they're going to link up together because they really like each other. Whereas all of the other molecules, they might either go link up with other molecules or they'll get excluded from the water's network. So you're going to end up with like little clusters of your salt, high concentration of salt over here, and then a bunch of water over here. And unlike other molecules, water actually when it freezes, it actually expands. This is because it has this like ability to form these like hydrogen bonds. And because of the shape of water and its ability to form these bonds, which are these like partial charge attractions, so the oxygen is partly negative and the hydrogen is partly positive, and they have this special arrangement where they have this type of attraction we call a hydrogen bond, much more in other posts. But because water can form these, and because these hydrogen bonds are strongest when things are aligned, when water forms a network, it does so in a way that like takes up a bunch of space. And your protein might seem like this big solid thing, but really there's just all these channels of water flowing through it. And this water, if you let it freeze, well, now you're going to have like things expanding inside of all those channels through your protein, which is not a good thing. And because when water was forming those networks, it was excluding other things, then those other things are going to get pushed into other regions, and you're going to have this really like weird mix. They're not freezing in place. And when you go to like wake up your protein, then it's going to wake up in an environment that it was not what it was when you froze it. And so different salt concentrations, different all sorts of things, and then potential damage because the water expanded. So these are all things that we want to avoid. And we can avoid this by not letting the water form those networks. So just a little on the terminology. So when we talk about like a solid, a liquid, or a gas, they differ from each other in how well the molecules can move apart from one another. And so this is going to depend on how sticky the molecules are for one another, and water is really sticky for other water molecules, and it's going to depend on how much energy they have. So if you imagine our molecular dance, imagine that these molecules are like loner geek people like me who would not want to be at a dance. So they're going to want to run to the exit. So molecules really like to be free. And they have this freedom from one another in this gas state. But it takes energy to do that, because you have to basically, if you imagine they're trying to escape for the door, and then every time they get near the door, then someone pulls them back in and they have to like wiggle their way free. So if you need energy in order to do that. So if you don't have enough energy, then you're stuck being a liquid or a solid. In a liquid, they can slide past one another, kind of like if they're swing dancing and they're changing partners, they're going towards the door, but they join up with another partner. So in a liquid, the molecules are sliding past one another. And then in a solid, they only have enough energy to vibrate. So when they're stuck in a solid, you would want to be stuck with the people you like, with the molecules you like. But in order to do that, you need to find those molecules, and you need to have time to find them and link up and all of this stuff. So we can prevent this. So when they link up in this optimal way, where it's like they're like this orderly network where everybody's with the people that they like in this big network, and so it's all like fair share. And this is what we call a crystal, and has this orderly like lattice. So it's like geometrically consistent units throughout. But you can also imagine that if you were to, they can lose the energy that they need to move past one another, but they didn't have time to organize. When we prevent this like crystals from forming and we instead get this like glass state, we call this vitrification. And we can do this by adding cryoprotectants, so like glycerol, like I was talking about, and I'll tell you more about, and or cooling it really quickly. So what happens is that cryoprotectants, you can think of them kind of like chaperones at the dance, that are kind of like getting in between people, making it harder for them to link up with one another. So even if the water had enough time to find, the water molecules had enough time to find one another, they couldn't, because it's harder to find those people because you have your chaperones like pushing in between them. So this is a really great article, Practical Macromolecular Cryocrystallography, the glass transition temperature, or this like TG, which is like, it's like a temperature, but it's actually like a temperature range. And in this range, you'll get that vitrified glass amorphous solid stuff that we want. Basically, what you want to do is you want to bypass the icification and get to the vitrification. So instead of like freezing in this solid crystal form, you want to get into this glass form. So what you want to do is be able to make it easier to get here, which you can do by raising this temperature and by lowering this temperature. So there's more like wiggle room in between them. And this is what cryoprotectants can do. So as I'll show you in a minute, they lower the freezing point, this freezing point depression, we call it, and they raise the glass transition temperature. So basically they'll get more overlap. So you can see here the glass transition temperature of pure water is 136 Kelvin. And with cryoprotected water, you have 155 Kelvin. So you're raising this and you're lowering this, making it easier to bypass to go from like the liquid form, bypass the ice forming and get into this vitrified state. So there are some common cryoprotectants that we use, but like glycerol, ethylene glycol, which is the classic antifreeze, and like propylene glycol. So I'll tell you more about why we use these, but really the thing is you could use anything because it's a colligative, this freezing point depression. So like lowering that freezing point is what we call a colligative property. And a colligative property is something that depends only on the number of dissolved particles and not the type of the particles. So it doesn't matter who your chaperones are. Well, I mean, there's regions that matters, and we'll get into some of those. But in terms of the freezing point depression, you could have any sort of molecule in there and it would do the same thing, which is why, for example, people salt roads. And so the salt is going to lower the freezing point to prevent the water from freezing and making ice and stuff. And they add salt for this because salt's really good, because what it does is it actually dissociates. So you put in sodium chloride, and when it dissolves, it also dissociates, so you get sodium and chloride. So now you have two things, and our colligative properties depend on the number of molecules. So now you have twice the number of molecules you put in, or the number of particles, and now you have twice the number of particles that you put in. So
That's great for the roads and it's cheap. Or I guess it's, well, I mean, I wouldn't say it's great for the roads because it can also be bad for wildlife and stuff. I'm not going there. I have another post on the salt stuff. But right now we're talking about why we wouldn't want salt for our proteins. And so basically we carefully make our buffers, so our protein solutions that like the pH buffer. So basically we carefully make our buffers so our pH stabilized salt waters that we want our protein in, it has a certain concentration of salt. And we choose that concentration of salt because it's like our protein's happy at it, or it's physiologically like relevant or something. But basically, proteins can act weird if they're in too little salt or they're in too much salt. And so we don't want them to be in too much salt. So too much salt and the proteins can actually clump up, or they can cause other problems. Salts, like as we saw, they dissociate, and so you get these positive and negative charged things, and they're floating around, and then your protein has these positive and negative charged things. So your protein might kind of interact with those and have different things and all sorts of stuff. So we don't want to add salt. We want to add something that's as like generic as possible, so we add something that's kind of as water-like as possible. And so typically, often we add glycerol. This is like the biochemist's go-to antifreeze. The downside is it's viscous and syrupy, and bacteria like it too. So let's talk about how we work with glycerol.
100% glycerol is super duper viscous, and so you don't want to try to pipette it. If you try to pipette it, then it's going to have difficulty, and your pipette is like, it might not suck it up, it might suck it up too far. When you try to push it out, then it doesn't go all the way out, then you end up with problems. So you want to use, it makes it a lot easier to work with if you have a solution of it, like 50% is like totally watery, and you can also, like 80% is still pretty easy to pipette. So what I do is I make a 80% glycerol solution, and I actually like syringe or vacuum filtered it. It's I mean, it's not like fast, but it still goes through the filter, and this way you prevent glycerol a lot of I mean, like bugs and stuff like sugar too. So you want to you can sterilize it with the filtering, so that you don't introduce anything you don't want into your protein. You don't want stuff growing in there. Sometimes, so how do you make this solution though? So what I like to do is I put liquid into like a graduated cylinder instead of trying to pipette out a certain amount. I use a graduated cylinder and I put in like the amount of liquid that, so I would put, like, if I was making 100 mils of 80, I would do like 20 mils of water or whatever the buffer. You can make one in the buffer that you're using, so that you don't introduce too much of the water when you're trying to add the glycerol, especially if you're using like a high concentration. So if you're freezing at like 50% glycerol or something, you don't want to then be adding a bunch of water. You want to add use your buffer to do the dilution, because you're already adding like a ton of glycerol, and like your protein needs a little buffer too. So I would put in like 20 mils of water or buffer, and then fill it up to the line. So just like pour in the glycerol or pipette it in into the center. So make sure you don't like drip it down the sides of the tubes, like into the center, and the water level or the liquid level will rise. Let it rise until the meniscus is the line, and then you want to mix it. So I paraffin over the top, and voila, invert, mix it that way, and now you have your glycerol solution that you can add to your protein.
Different proteins, you will need different amounts of glycerol potentially. When I'm just freezing like a normal protein or whatever, a pretty stable protein, then I freeze normally at 10% glycerol. But when I'm, like the other day when I was purifying a kinase, so like an enzyme, I need to make sure that its activity is very well preserved. I need to be able to wake it up easily. Then I froze it at 50% glycerol. So typically what I'll do is I'll calculate from like my 50% or my 80% glycerol stock, how much I would need to add of that I'll calculate how much protein I have, calculate what the final volume I want. So if I have 2 mgs of protein and I want to freeze it at 2 mgs per mil, then that would be a mil. And then I need to calculate how much of the glycerol with that volume, and then I subtract those and those, and then add buffer to put in the difference. And then it's time to freeze them, or to flash freeze them, to vitrify them. So our goal here is to add those cryoprotectants to make it harder to find one another, lower that freezing point, raise that glass transition temperature, and cool it really, really quickly so those water molecules can't find one another. And for this cooling really, really quickly, we can use liquid nitrogen. So liquid nitrogen is really great in that, unlike other gases, we can keep it as a liquid, but it's going to turn into a gas pretty quickly. So we keep it in these storage dewars. And basically, this is going to keep it in this liquid form, and then we can pour it into things. But then once they come into contact with things like the protein in our tube, heat flows from warmer to colder. So the stuff in the heat from our protein is going to flow into the liquid nitrogen. Liquid nitrogen is going to become gas nitrogen, but our protein is going to freeze, or it's going to vitrify. You want to be really careful when you're working with liquid nitrogen. And you should wear safety goggles, where, yeah, this was not a good picture, but you should be wearing safety goggles and better gloves, thicker freezer gloves. Biochemists, my thumbs are sometimes Siri doesn't or sometimes my Touch ID thing doesn't recognize my thumbs because I have freezer burn because I don't listen to my own advice. So you can pour the liquid nitrogen out into one of these foam thingamabobs. And this is where having this plasticky thing helps with keeping the tubes in line.
So our campus machine shop custom made these for us so that these go in your ice, your tubes go in here, and then you can dunk this onto liquid nitrogen and freeze it like this, so you don't just plop in your tubes. When you just plop in your tubes into liquid nitrogen, well, one, then you're gonna have to fish them out, which is dangerous because your fingers are precious. Number two, if your tubes you want your tubes to be vertical when you're doing this, or else when you put it in the liquid nitrogen, then your tubes are just going to go sideways, and then you're going to end up with your protein frozen all over the side, which is the same reason why you want to centrifuge your protein down before you freeze them, so avoid that.
So when I'm storing my protein, I typically have way more than I would want, hopefully have way more than I would want to use at a single time. And you want to avoid freezing and thawing your protein, because although we have the cryoprotectant in there, there's gonna be some damage every time we do this freeze thaw, and we want to avoid that as much as possible. So freeze little single-use portions type of thing. So how much you kind of know how much you would want for a various assay, so certain experiments. And then do 20 microliter aliquots for this, 10 microliter aliquots for this. It all just depends on your protein and your uses and that sort of thing. And if you have something where you want a ton of aliquots, so this is my kinase, I want lots of aliquots, because especially for an enzyme, you really don't want to be opening, waking it up and sleeping, wake, sleep, whatever. So I do it in strip tubes. And then I can just cut off a tube when I'm ready to use it. And using a repeater pipette makes it really easy to do a bunch of racks and keeping it in this cold and this ice. When you're working with proteins, you want to always keep them cold, keep them on ice. Don't hold the tube from the bottom, because then you're preventing the coldness, you're adding warmth. So I have this plastic holder, and then I have my tubes so that the caps don't clash. I actually skip a row, but then if you're doing a bunch, then once you cap them, then you can move them over. But another thing just to be careful of is that when you're capping them,
if you're capping it and you push down too hard, like this part can like fly open like that. So you want to make sure that you're holding down with one hand when you're capping it with the other, so that all your stuff doesn't just go like flying everywhere. True story. They also make these like chill blocks that you keep in the freezer, and then so I use these when I'm doing really tiny aliquots. I'll make them in strip tubes. And then I'll use the repeater pipette to like in each of the strips, and then cap the strips. Capping the strips is like the hardest part. We used to have this like roller thing that helped you like put the lids on, but I don't know what happened to it. But yeah, these things are pretty cool for freezing samples as well, if you don't have like one of these things or whatever. And before you freeze them, you're going to want to give them a quick spin in like a pulse centrifuge or something, so that if you have all the liquid on the walls, then everything's just going to get like stuck on the walls and you're going to lose a lot of protein. You want everything to be nice and spun down into the bottom before you go into the liquid nitrogen.
You also want to make sure that you label your tubes well. So originally I was really excited. I found these labels, like the label maker. I could print out all these labels, and then the labels would pop off. And even though I tried a bunch of different brands, I was not happy. So I just like write on the tubes with really tiny letters. But I got smarter, and instead of trying to aliquot all of it at once, instead I'll make like 10 or so aliquots, depending on what I plan to do with this protein. And then I'll keep bigger portions. So maybe like 200, I'll have like 5 200 microliter aliquots, which I call like my stock. And then like 10 of the 20 microliters aliquots. And this way, when I run out of these, then I just have to thaw one of these tubes and then aliquot them out again. In terms of what to put on the tube, so I put like the construct number. That's how I keep track of all my different proteins, is they have a number. And then the concentration and the date. The date is super duper important because it's going to let you check back to your notes. And if there's a problem with one of your preps, you'll be able to tie it back and get rid of that or investigate it further. And so I also, whenever I'm doing an experiment, I take note of the prep date for the protein that I was working with. It really is such a great feeling when you have your protein frozen, and of course put in the -80 freezer, which is where we typically store our proteins. In undergrad, we had our -80 freezer break down, and then the replacement broke down, and then we got like a new one, and we got it fixed, and then it broke. Yeah, basically we had a lot of -80 problems, and there was a lot of dry ice to the rescue sorts of things going on because we only had like a single -80. Here we have like 3 -80s in our lab alone, like in my lab. It's crazy. And in addition, we have some storage dewars. So like these. So this one's not a storage dewar. This is like one that we actually use for like pouring out the liquid nitrogen. But we also have just like little guys that we use, for example, when we're shipping protein, shipping crystals. And so these typically, they're smaller. They have they have things that you stick in them, basically, like little canes. And you can store things in these like racks and stuff that are in there. We had something like this in undergrad, and I needed to flash freeze a protein, which this dewar was not conducive for. So I took some wire, and I took my protein tube, and I like put wire around the tube and kind of like fished it in. Worked great most of the time. One time though, a tube like fell in there and was lost for forever, and for, I don't know, it probably emptied the thing at some point. I wonder what happened to that tube. It was probably like, I don't know what happened. If it stays in liquid nitrogen, I don't know. But anyway, yeah, so be careful if you're doing that. Happy purifying and freezing, and hope this was helpful